Thank you, Julien, and hello, everyone. So first, a disclaimer. So this is the first and perhaps the last time I'll give this talk, so I don't know how long it will take. So to be efficient, I will focus first on mathematics and go as straight to the point as I can. And I will give comment and about quantum mechanics and physical interpretation in the end. So I will start with something which in principle you are all supposed to know, which is the diagonalization of Hermitian matrices. So this means that we are working on the space which I will denote by H, which is Cn, equipped with the inner product, with the canonical inner product, so which is you conjugate U, you transpose, and you multiply by V. So if you prefer in coordinates, this is sum of Uj bar Vj, whenever U and V are vectors in Cn. And I will pick H, capital H, to be an Hermitian matrix. Meaning that if you take the transpose and conjugate, so which is by definition the adjoint of H, you recover H. So Hermitian is this equality, H equal H star. So you get a self-adjoint linear operator in the sense that if you compute the inner product of HU against V, you get U HV. Okay, and a result which you are supposed to know is that there exists an orthonormal basis EJ, orthonormal basis of Cn, such that if the spectrum is denoted like that, you have an orthonormal basis of your space which diagonalize the matrix in the sense that each Ej is an eigenvector of H for the eigenvalue lambda j. Yes? Okay. So Hij is lambda j Ej. Okay, so this is in principle a well-known result, and there are several consequences. So first, if you have an orthonormal basis, any U in Cn can be written, so write U is the sum, so the coefficients of U along the basis Uj are obtained by just taking the inner products of U against the Ej's, so you get something like that. So in particular, if you compute the norm, the square norm of U, this is just the sum over J of EJU in modulus square. So this is the first observation which has nothing to do with H. And the second one is that once you can diagonalize an operator, you can easily take functions of it, in particular exponentials. So if you pick any z in the complex plane, you can define the linear map EZH, which is defined by the fact that when you apply it to a vector u, it is defined as the sum over j of EJU times EZ lambda j EJ. So this acts on any eigenvector trivially by the multiplication by this constant, and you can define the operator on the whole space. Okay. So now, before diving into the topic of the harmonic oscillator, I will give an analog of this result in infinite dimension, which you know, but maybe which you are not really aware of, because when we teach Fourier series, and especially in second or third year, maybe we do not insist on the operatorial point of view, but okay, so the next section is about Fourier series. So here, I will try to be parallel to this first paragraph. So here, we will consider a Hilbert space H, which is L2 of minus pi, and the inner product. So now the elements of L2 are functions. So if you compute the inner product of two functions, by definition, it's really 1 over 2 pi. The integral between minus pi and pi of u of alpha conjugate v alpha d alpha. And that's it for the moment. So what you have more or less learned. Okay, maybe I will introduce some notation before. So we'll let Ej be the function Ej of alpha is exponential ij alpha, and here j belongs to z. So what are the Fourier coefficients of u, of functions? Well, if you remember your course on Fourier series, this is by definition 1 over 2 pi, the integral between minus pi and pi of e minus I j alpha u of alpha d alpha, and this is nothing but the inner product of Ej against u. So this is the analog of this kind of guys. Moreover, you have probably seen that if you compute 1 over 2 pi, the integral between minus pi and pi of e minus ij alpha e I k alpha d alpha, which is nothing but here again the inner product of Ej and Ek. This is a Kronecker symbol, meaning this is 0 if j is different from k, and 1 if j equal k. So this tells you that this family of functions, the family of the Ej's, is an orthonormal system in this Hilbert space. If j equal k, you get Ej against Ej. This is the square norm of Ej. This is 1. So the vectors are normalized. And if you pick two different vectors, they are orthogonal because their inner product is 0. So very much like you may have orthonormal basis in finite dimensional spaces, here you have this fairly natural orthonormal system. And what how can we interpret the decomposition of a function u in Fourier series? So here I do not specify any assumption on u because it depends on where you come from. If you are in M2, you know that you can pick any u in L2. If you were in licence last year, maybe you only know the result when u is piecewise continuous and perhaps some regularity. I don't want to set any assumption here. I mean, pick your favorite assumptions for the expansion in Fourier series. But basically, what it says is that when you write something like u of alpha is the sum over j in z of the Fourier coefficients times eij alpha, this is actually just saying that u is the sum over j in z of the inner product of ej u ej. So this is the infinite dimensional analog to this identity. So decomposing a function in Fourier series is just writing in some sense decomposing the functions along an orthonormal system in this infinite dimensional Hilbert space. And to complete the analogy with respect to the first paragraph, here there is a hidden self-adjoint operator. So moreover, if you let h to be 1 over I d over d alpha, so this is the operator of differentiation with respect to alpha, it is completely elementary to check that h applied to ej, this is just j ej. You see, if you differentiate here in alpha, you will split ij in front of everything. If you divide by a, you just have the j here. So the ej's, they are eigenvectors of this linear map. So in this sense, Fourier series are an analog to this kind of result for the specific operator, which is a differential operator in one variable. And perhaps one more comment. Here I choose my matrix to be Hermitian, so self-adjoint if you prefer. And here again, this operator is in some sense self-adjoint for the following elementary reason, at least from the formal point of view. So 1 over I d over d alpha is formally at least self-adjoint in the sense that whenever u and v are C1, so in minus pi, so I will close the interval and ask that they are periodic. So if you consider periodic functions, which is the one you consider when you do Fourier series, if you assume that they are smooth on minus pi or actually on R, if you compute the inner product of h, u, and v, what is it? This is 1 over 2 pi, the integral between minus pi and pi. So hu is 1 over I u prime of alpha, v alpha, d alpha. And if you integrate this by part, which is allowed because you have C1 functions, so what you get is 1 over 2 pi times, so I integrate this guy, so I get 1 over I u conjugate v between minus pi and pi, and minus the integral between minus pi and pi of 1 over I u conjugate and v prime d alpha. Since the functions are periodic, their values in pi and minus pi are the same, so this cancel out. And here you have a minus, but 1 over I conjugate is I, and so we just use the observation that 1 over I is minus I, and 1 over I conjugate is I. So playing with this relation, you see that you can drop the minus here and put the 1 over I here, and you get 1 over 2 pi, the integral between minus pi and pi of u conjugate 1 over I v prime d alpha, and this is exactly u of hv. So Fourier series, at least here I'm dropping all the assumptions on the conditions under which we have convergence. Where can we do that? So I give sufficient elementary conditions. This can be generalized, and this is part of the program of the Master 1 to understand when you can do that. But just at least from the algebraic point of view, this says that when you have Fourier series is an example of diagonalization of a self-adjoint operator, namely this differential operator, in an orthonormal basis for a suitable Hilbert space structure. Okay, and now, so the purpose of the talk is to explain how to find in a very really elegant and simple way how to diagonalize another important differential operator, which is the harmonic oscillator, the quantum harmonic oscillator. I think that this calculation, which is nowhere in the standard program, I mean at least from master, is actually something which is good to know, because somehow it touches many fields of mathematics. So I think for your culture it can be interesting to have seen what I'm going to present at least once. And if it's of no use for you, at least you will have sandwiches after the talk, so you have not completely lost your time. Okay, so this is the third paragraph. So the quantum harmonic oscillator. So as before, so we need a Hilbert space, so a space, a complex space equipped with an inner product, and which is complete for this, and relatively to the norm, the associated norm. So here our Hilbert space will be L2 of the whole line, so equipped with the usual Lebesgue measure. The inner product is the inner product of L2, so if by definition the inner product of two functions in L2 will be the integral between minus infinity and infinity of u of x conjugate v of x dx. And what the quantum harmonic oscillator this is the differential operator of order 2, which is given by so 1/2 of h over I d over dx square plus x squared, and I will denote it by capital H. So H, you can imagine this is for harmonic, but actually this is for Hamiltonian. So more explicitly, or slightly more explicitly, I hope this is clear that way, but the action of H on a function, so the 1/2 is a normalization. So here you differentiate twice, you multiply by h over I squared, so you get minus h squared u prime prime of x, and x squared acts as a multiplication operator on function, so plus x squared times u of x. This is the sense of this expression of the oscillator. So here, I will comment later on that, but H, this is it represents the Planck constant, which is and this is one of the in practice, in what we are going to do, H plays no role. We could take H equal 1 and you. But if time, I don't know. If I have time, I will try to explain the role of H later in this talk. But let's say it's some kind of a quantum decoration of our operator. So H, this is reminiscent, say, of the Planck constant. And so what we want to do, in analogy with the first two paragraphs, is to find the spectrum of this guy and find an orthonormal basis of this guy. And a priori, this is not an easy task, because even in finite dimension, finding the eigenvalues of a matrix, namely finding the roots of the characteristic polynomial, it's never easy, at least for me. In 2D, okay. Afterwards, it's always difficult. And in infinite dimension, it's even more difficult because you don't even have a characteristic polynomial. And if you go back to the problem of the Hamiltonian in Fourier series, here this is H. This is just, if you want, E prime J equal G EJ. This is solving constant coefficient differential equation of first order. So this is not completely obvious because it's not really a Cauchy problem, but maybe there is hope that you can guess something because we know how to integrate constant coefficient equation in principle. But here you have you will have second order differential equations and with non-constant coefficients. So this is not a priori this is not a simple object. But as you will see, there is a very, very nice approach which provides in just a few lines a complete orthonormal basis of eigenvector of this operator. So it goes the following way. So okay, so we need to introduce two more objects, which are A, which will be called the creation operator. Sorry, we'll start with the annihilation operator. And this is the first order differential operator, which is, so there is a normalization, 1 over square root 2 of h d over dx plus x. and A star, which is the so-called creation operator, and which we define as 1 over square root 2 of minus hd over dx plus x. So again, if you are not, or maybe if or as you may not be very familiar with the notation of differential operators, this means that the action of A on a function u is just h over square root 2 u prime x plus x over square root 2 u of x. And similarly for this guy. So the notation star here is not, I mean, it is natural because, at least again formally, this guy is the adjoint of this guy for the inner product. So this will be computation 1. So for suitable u and v, so meaning these are functions which are smooth, which you can, which belong to L2, well, functions for which all the calculations which are going to present are justified. For instance, you can take functions which are C1 and which vanish outside an interval, or if you have started your the course on distributions for those who are in M1, you can take test functions, C0 infinity functions. So for suitable u and v, if I compute a u v, so by definition this is, so I want to see that this is u against a star v, which is a natural relationship between an operator and its adjoint. So the reason basically is that when you compute x u of x v of x dx, here x, which belongs to R, so you can move it away from the conjugate and put it in front of v. So this is just xv x dx. So the adjoint of x in this sense is x. So when you take the adjoint of this part, you take this one. And when you compute the integral between minus infinity and infinity of u prime of x conjugate vx dx, if you integrate by part, so formally you will have a contribution of u v between minus infinity and infinity, but since you take good functions, this is 0 because they vanish at infinity. And from the integration by part, you get a minus integral between minus infinity. Sorry, I will. When you integrate, the prime goes on the v, but up to a minus, and this is why here you get a minus when you do this process. So the creation operator is the adjoint of the annihilation operator. And then you have two other very useful algebraic identities. Namely, so the first one, so computation 2, what is A star A? So if you compose those two operators, so there is 1 over square root 2, which is squared. And so to the left you have A star, so you have minus h dx plus x, and here h d over dx plus x. And so you get 1 over 2. So this guy, with this guy, you get minus h squared d2 over dx squared. This guy with this guy, you get x squared. And you have the cross term, so you have minus h d over dx x plus x h d over dx. And this guy, so this is not 0. This is not 0 because the multiplication by x and d over dx, they do not commute. But if you compute d over dx of a function, xu, by the Leibniz rule, you get u plus x du over dx. So here, the difference between the two is just the multiplication by 1 as an operator. So this difference, actually, this is minus h, minus the multiplication by h, if you want. So up to this constant, you recover the harmonic oscillator. So this gives, so A star A, this is h, so half of this guy, here, minus h over 2. And similarly, you can compute A star. So you just swap the two and do exactly the same calculation. So you will get the same up to the sign which are changed here. You will get plus h. And you get that A star is h plus h over 2. H over 2, if you want, it's h over 2 times identity. So this is a linear map. H over 2, it acts as just the multiplication by h over 2. So as an operator, if you want, you put the identity, but I will omit it most of the time. And now from these two observations, we shall see that getting an orthonormal basis of eigenvectors of H and guessing its spectrum is almost trivial. I mean, it's trivial when you know how to do, of course. Afterwards, it is trivial, but it means this is something very beautiful. So, one comment, perhaps, here. If you think by analogy with what you know for matrices, this guy is automatically self-adjoint. If you get remark, so at least formally, if you compute the adjoint like you would do for the transpose of matrices, say, you know or must know that you will take the adjoint of each term of the product, but reverse the order of the terms, so of the factors. So to the left you put the adjoint of this guy, and to the right you put the adjoint of the first one, and the adjoint of the adjoint is the operator itself. So this guy is self-adjoint, at least in this formal sense, and so H is self-adjoint too, because this is the same up to this guy, which is the identity up to the real factor. So this guy is self-adjoint for trivial reasons, and so this one is obvious reason because again up to this constant, it is of the form A star A. So H is self-adjoint. And now how to guess an orthonormal basis plus the spectrum of eigenvector of H plus the spectrum. Okay, so I will just rewrite those definitions here. So A, this is 1 over square root 2 h d over dx plus x, and A star, this is 1 over square root 2 minus h d over dx plus x. So, first, first observation. As I said, second order differential operators with variable coefficients are a nightmare in general. But first order linear differential equations, when they are scalar, they are simpler. We know how to integrate, to find solutions, and so on. In particular, if you look at this expression, see here, if you find a guy which is in the kernel of this operator, so if you find a solution to the equation h d over dxu plus xu equals 0, if this guy applied to u is 0, then this guy applied to 0 is 0, and you will find an element of the kernel of this operator. So this is an eigenvector of this operator. And this will give you an eigenvector of H, because this is trivial. So everybody is an eigenvector of H over 2 times identity. So, so the first and main character of this story, so I don't solve the ODE, but rather gives directly the result. Observe that E minus x squared over 2h, so the Gaussian up to normalization, belongs to the kernel of A, and the name annihilation. The annihilation operator applied to the Gaussian gives 0. It annihilates the Gaussian. Well, actually the name creation and annihilation are deeper than that, but this is the first, say, justification of the name. I mean, you can see it right away. If you apply d over dx to this guy, you will split the derivative of x squared, which is 2x divided by 2h, so minus x over h, and if you multiply by h, you get minus x, plus the x, which is here, you get 0. So, if you compute h of this Gaussian, what do you get? So h, I will write it in terms of this guy, so this is a star a plus h over 2 applied to the Gaussian. So this is a star a e minus x, sorry, there is an h, plus h over 2 e minus x squared over 2h, and this is 0. And so what you get is h over 2 e minus x squared over 2h. So you have an eigenvector of h, with eigenvalue h/2. So after normalization, psi 0 of x, which will be pi h minus 1/4 of e minus x squared over 2h, belongs to L2. It has norm 1, and it is an eigenvector of h. Okay, this is just one eigenvector. And since we are in infinite dimension, we expect, we have to actually, find a sequence of eigenvectors. So we have just one, but we need to find infinitely many. And so I will try to state the theorem. So the sequence psi n, so n in so defined by induction. So psi 0 is of course psi 0, and then I will define psi n plus 1. Can you read in the back here? Okay. Psi n plus 1, this is 1 over square root h times 1 over square root, so let's check my notes, n plus 1, creation operator applied to psi n. So the statement is not complete. So the claim is that you can define by induction a family of functions in this way. You have psi 0, it's a smooth function. You apply a star, which is a differential operator, so you still keep a smooth function. So psi 1 is a smooth function. So then you can apply a star to psi 1 and get psi 2, etc. This way you can compute a family of a sequence of smooth functions, and they are this sequence so is an orthonormal system of L2. So meaning each of them is normalized, it has norm 1, and if you pick two different guys from this sequence, they are orthogonal. It's an orthonormal system, and of eigenvectors of h, and more precisely, if you compute h of psi n, you get h times n plus 1/2 of psi n, and the spectrum of h, is this sequence, is a set of all h n plus 1/2 when n is a non-negative integer. So this is just a claim. But now I will explain why it's true. will check, I will show you that psi1, so when n equals 0, psi1 is an eigenvector for the eigenvalue h times 3/2. And then all the calculations are the same for other terms. If you understand the case n equal 1, you understand the whole proof. So for n equal 1. So let's drop the normalizing constant and consider a star psi 0. And we want to see that this is an eigenvector of h. So we compute h of a star psi 0. Now h, I can write it in terms of the creation and annihilation operator. So I will use this identity. So here you have a relation between h and this guy. So from, I don't know, I will call it 1. So using 1 here, this is a star a plus h over 2 applied to a star psi 0. So if I expand, I get a star psi 0 plus h over 2 a star psi 0. And now this guy, a star, this is almost h from the second identity. A star is h up to a trivial term. So this is a star, a star, so from this is h plus h over 2 psi 0 plus h over 2 a star psi 0. And now you are done because you know that h psi 0, this is h over 2 psi 0. You have another h over 2, so you get a star of h psi 0 plus h over 2 a star psi 0. And a star is linear, so you can move the h outside. And you get what? You get h a star psi 0 equals 3h over 2 of a star psi 0. So a star psi 0 is an eigenvector. Well, it's an eigenvector if it is not 0. But it is not 0 because you can compute explicitly a star psi 0. And for the eigenvalue, uh, 3h over 2. Well, it's an eigenvector, but it has not norm 1. So now I must compute the norm of this guy if I want the normalized version and explain where this funny coefficient comes from. But if you have ever orthonormalized a basis in I don't know R3 or something like that, if you have to compute the norm of the eigenvector which you have found, I mean it's not a difficult task, but you can. I mean, it's also easy to make some computation mistake, but here somehow computing the norm is very easy. So, moreover, what is the norm? So the square norm. So since we are in a Hilbert space, this is the inner product of a star psi 0 against itself. But now this is the adjoint, which if I move it here, I will change a star into a. So this is psi 0 against a star psi 0. And A star, this is almost H. Again, from this identity, from 2, so perhaps I will write it here. So using the identity 2, this is psi 0, H plus H over 2, psi 0. And so H plus H over 2 psi 0, this is H, little h psi 0. So you get here H times psi 0, the norm of psi 0 square, but this one is 1 because we have normalized psi 0 initially. So the norm, the square norm here is H. So if you want to get a normalized function, you have to divide by 1 over square root H, which is here. And for if you go upper in the spectrum, so if you really consider the induction, when you do the same kind of calculation for psi n, you will get H plus H over 2 applied to psi n. And since psi n has eigenvalue Hn plus 1/2, here instead of H you will get Hn plus 1, and so when you normalize, you get this term. But there is no more than that. Okay, so I don't know how much time I have left. Okay, no pressure. I mean, here I could say several things. Here, if I want to be honest, so a remark that the system is orthogonal. This is automatic because when you have, I send you to your course on the diagonalization of Hermitian matrices. When you have two eigenvectors associated to different eigenvalues for a self-adjoint operator, they are automatically orthogonal. So the orthogonality is for free. What I have not proven here, and which could be do rather quickly, but maybe it's not so exciting, is to prove that the system is complete in the sense that we have not forgotten any eigenvalues, because since there are infinitely many of them, there could be other. That could be a way to produce eigenvalues and eigenvectors, but maybe not all of them. But we pick everyone here, and the proof is not very hard. But since I want to spend a few minutes to comment on the quantum mechanical interpretation of all this and make connection with something completely different with the symplectic geometry, perhaps I will not insist on the completeness of the system. Okay, I will erase this part. So Julien, stop me whenever you want. So it's maybe the third section. Physical interpretation. So what you have probably met at least once when you were younger is the classical harmonic oscillator, which is this kind of picture. So you have a spring of stiffness K, and you have a mass at the end of the spring. And if you are on an axis and measure if x represents the position of a point, of the mass here, the kinetic plus potential energy of this system, so the total energy of your system, this is 1 over 2m p square plus 1 over 2 k x square. So this is the potential energy. And this is the kinetic energy. So P is the momentum, so it's in French quantité de mouvement, m times velocity. So if you replace P by mv, you get 1 over 2 mv square, which is the usual form maybe of kinetic energy, which you have, well, at least that was the usual form we used when I was younger, a long time ago. So here, this is the classical Hamiltonian, which describes the energy of the system when your particle, your point here, is at position x and at velocity or momentum p. So if we drop the physical constant, so the classical Hamiltonian is the function on phase space. So phase space here is just R2, namely Rx times Rp. This is a function 1 over 2 p square plus x square. So I set k and m to be 1 for simplicity. Now, so this is the. So this is, I mean, in a nutshell and in 1 second, this corresponds to classical mechanics, which is described by the law of classical mechanics. In particular, if you want to know the motion equation of a point, you know that you have this Newton law. M times acceleration is the force applied to the guy. But actually, you can rewrite this. So if so now if I pick m equal k equal 1 for simplicity, this is, you can write this second order equation as a first order equation by saying that dot x, so this is the velocity, this is p, because if m equal 1, p is the velocity. And if you differentiate p, which is the acceleration, you get minus x. And if I denote by t the solution to this system with initial data at t equals 0, which is a pair x0, p0, you can compute explicitly the solution, and you get xt pt, which is cos t x0 plus sin t p0 and minus sin t, perhaps my signs are wrong, I will just check, plus cos t p0, so no, that's correct. Okay. So this describes the classical motion. If you just look at xt, you have an oscillatory movement because it's period. I mean, sorry, there is this cos t and this sin t, and of course this corresponds to the fact that if you push the spring and leave the system evolve, your x will move that way. So in an oscillatory way. And so this is classical mechanics. But classical mechanics, it works at the macroscopic scale. I mean the one we can observe. But at the microscopic scale, if you want to study atoms, electrons, and so on, these laws are no longer available, and you have to use a quantum mechanical description of your system. And the analog of the classical harmonic oscillator in quantum mechanics. So quantum mechanics basically, how do you go from this classical Hamiltonian to the quantum harmonic oscillator, which I described before? Basically, you replace functions by operators. And P by H over I d over dx. So formally, in here, 1 over 2 p square plus x square, it becomes 1 over 2 h over I d over dx square plus x square, where x square is now seen as an operator, the multiplication by the function x square. And, okay, maybe I'm running out of time, so I will stop soon, but just in a word, I don't unfortunately have time to say a word on the quantum mechanical dynamics and connection between the classical and quantum one, but here what I just want to say is if you want to feel just one aspect of why this is reasonable, it's because for this Hamiltonian we have seen that we have energy levels. This corresponds to energy levels, and they are quantized. If you want to move from one energy level of the system to the next one, you have to move by a quantum of energy, which is of size h over 2. So unfortunately, I will have to stop. But say the last comment will be that quantum mechanics is something which is very rich and which provides a huge source of interesting mathematical problems. And this, the quantum harmonic oscillator, here it looks as it's just ordinary or partial differential equations, but actually it is connected to many other fields, like probabilities. If you see the Ornstein-Uhlenbeck process one day, this is the harmonic oscillator. This is connected to symplectic geometry. This is connected to representation theory. I mean, this is, you can see it in many places in mathematics. And why? I mean, because in quantum mechanics is a amazing, beautiful source of interesting mathematical problems. So I stop here and thank you for your attention.
This method of factorizing the Hamiltonian into two operators, one of which is adjoint of other. How far can we can we do similar things with other Hamiltonians as well? Like, is there any program where we can do some similar factorization of?
So I'm not sure I understood everything, but is your question something like can this be generalized in any way?
Yeah. For general Hamiltonians, not just.
Okay, so of course the beauty of the harmonic oscillator is that this is completely algebraic. We can compute everything. This is everything is more or less explicit. But yes, to some degree, I mean, there is a robust way to look at this. So maybe you cannot compute exactly the spectrum, or maybe you cannot get the exact form of the eigenfunction, but at least for 1D problems in 1D, or for integrable systems, but in particular in 1D, there is what is called the Bohr-Sommerfeld quantization rules, and which explain when you replace your x square, which is here, by a more general potential, how I mean, which energy levels somehow of the classical system you have to select to get eigenvalues of the operators. And so this is another say illustration of the quantum mechanical aspect, namely that here again, if you look at those Bohr-Sommerfeld quantization rules, you will see that again the energy levels, they are separated by something proportional to h basically, and say that at the classical level, I mean, the system can exist on any energy level. I mean, if you choose appropriately the initial speed and initial position, you can. But here somehow you are quantized. But I mean, okay, I could say many things, but perhaps the closest to this is the Bohr-Sommerfeld quantization rules.
That's not really a question, but you talked about the connection with symplectic geometry, and I was wondering if you could quickly say more about it.
Yeah, so there is one aspect which is not my comfort zone, but basically the connection with algebra in representation theory, that this can be useful to give a representation of the symplectic group. So that's the first connection. But the one which I had in mind is, as I said in the beginning, you can consider exponential of self-adjoint operator, and if you consider say this guy, so here h, this is a harmonic oscillator. So this allows to solve the time-dependent Schrödinger equation, and what you can see is that you have an expression for the solution to this problem, and this is so let's see something like that: psi t x p 1 over h u hat of x over h dp n times 1 over cos t to some power, perhaps 1/2, does not matter. So u hat is the Fourier transform, but the important guy is the psi here. And the psi, so I can give you a complete, I mean, an exact expression for this, but the point is that here, if this flow, if I denote it by phi t, so it depends on the initial data x naught and p naught. If you know symplectic geometry, this guy is symplectic. And it is symplectic, and it is on the classical side. I mean, it's for the classical Hamiltonian. Here we are looking at the quantum Hamiltonian. And this function psi is what is called a generating function of this symplectic guy. Meaning, it means that phi t of d psi over dp p, this is d psi over the, no, sorry, this is x, d psi over dx. So psi depends on t, so here everything depends on t. But you see here, there is a connection between this guy, which is a quantum object, the phi t, this is a classical object from classical mechanics, and the description of this propagator is given in terms of this phase. I mean, this is something which is real valued. And you have this connection between this phase, which describes the quantum guy, and the classical one. And this is one elementary, yet very deep connection between the quantum and the classical world. And psi, this is a generating function of this flow. And this flow, it is a symplectic map on R2. This is where this is a kind of, this is an example of where you have a connection with symplectic geometry. But I mean, there is plenty of it actually. Just because on a Hilbert space, which has a complex structure, you have some symplectic geometry in finite dimension if you want. So there is symplectic geometry everywhere, but I particularly like this one, which makes a connection between the quantum and the classical world.
Thank you.
about why the system, orthogonal system, is complete?
Yes. So what you can see by induction from the construction of the psi n, you can see that psi n is exactly a polynomial of degree n times the Gaussian. So this means that when you have the system, the whole system, which I described, you can write any, so xk times the Gaussian in terms of the psi n. You see, because if you have a family of polynomials of increasing degrees, 0, 1, 2, etc., you get a basis of all polynomials. And so from this, you can show that if u is orthogonal to all psi n, that will imply that u times xk times the Gaussian is 0, or n, is 0 for all n. And the trick, okay, it's formal here. By the way, this is a not especially difficult, but this is an exercise on Lebesgue's dominated convergence theorem. If you have u xk psi 0 equals 0, that tells you that the integral of u x xk psi 0 x dx is equal to 0 for all k. And now, if you multiply by tk by, so you replace xk by itx k. So I and t are just constant, so they can move inside. And if you sum, you can show that the integral of u of x conjugate eitx psi 0 x dx is 0 for all t. You see, if you expand the exponential into a series, you get powers of xk. So all terms if you move the sum outside the integral sign, all terms are 0. And so this tells you that this is 0 for all t. This tells you that u conjugate psi 0 Fourier transform at t, this is 0 for all t. So the Fourier transform of this guy is 0, so the guy is 0, because the Fourier transform is injective. That's the idea. It's not very difficult to justify, but the point here is when you expand the exponential into a series, you must make sure that you have the right to swap the sum and the integral, and this is where you have dominated convergence. But that's all. And so this means that the orthogonal of the subspace generated by the psi n is 0. And so you get the whole space, basically.
In quantum mechanics, what do the eigenvectors represent?
Well, so I'd say, so if you look at the periodic classifications of elements, the Mendeleev chart, so there are numbers which represent basically energy levels of the fundamental level of the particle, and perhaps excited levels. So the first eigenvalue, the first eigenvector at least, it describes the fundamental state of a particle, so the most stable one, if you want, because particles, they are described in terms of functions in L2. If you take their modulus squared, it describes the probability that you find this. It's a density probability which describes where you can find the particle in the space, and so the different eigenvectors of the quantum of the harmonic oscillator, basically they describe the excited states of a particle described by this mathematical say model of a quantum particle, which would, sorry, I don't find my words. They describe the excited states of the particle given by the harmonic oscillator, if you want. If you bring some energy to your particle, you will excite it, and it moves from the state psi 0 to the state psi 1, etc. I'm sorry, it's not perhaps not very convincing. Maybe you should look at a physics textbook, which will say it. I mean, rapidly better than me. But basically, the psi, they are the wave functions, and if you take their modulus to the square, they are probability presence of a particle in some state, and the higher you go in the spectrum, the more excited your particle is, if you want.